In this practical, we investigated the motion of a dart launched from a projectile launcher. The goal was to measure the dart's initial velocity, analyze its trajectory, and estimate the effect of air resistance on its motion. We also explored the relationship between the launcher's spring mechanism and the dart's launch speed. The experiment involved the tracking of the dart's motion using a video application, analyzing the data and applying physics principles to interpret the results. Measuring the initial velocity. The dart's initial velocity was determined by analyzing its motion using a video tracking application. The launcher was fired and the dart's trajectory was recorded at 30 frames a second. 2 points on the trajectory were selected. Using these 2 points, we calculated the horizontal and vertical components of the initial velocity. The horizontal velocity was found using a formula where the x delta is the horizontal displacement and the t delta is the time interval. The vertical velocity was calculated by accounting for the effect of gravity. Using vertical displacement, delta y, and time interval, we determined the vertical velocity at the first tracked point and then backtracked to find the initial velocity at launch. Estimating air resistance. The theoretical range of the dart was calculated without considering air resistance. This was compared to the actual measured range to estimate the effect of air resistance. The theoretical range was determined using the initial velocity components and time of flight for test 1. The theoretical range was 4.89 meters, but the actual range was only 1.8 meters. This difference is due to air resistance, which opposes the dart's motion and reduces its range. To quantify air resistance, we assumed constant deceleration and used the kinematic equation AX is roughly equal to 3.5 meters per second. This declaration represents the effect of air resistance on the dart's horizontal motion. The launcher uses a spring to propel the dart. The spring's elastic potential energy is converted into the dart's kinetic energy at launch. Using the principle of energy conservation, we relate the spring's compression distance to the dart's initial velocity. If the uncompressed length of the spring is 5 centimeters, the compressed length during launch is 2.13 centimeters. This calculation links the launcher's mechanical design to the dart's launch speed, demonstrating how the spring's properties influences the projectile's motion. Physics principles. This practical demonstrates several key physics concepts. First, projectile motion is governed by the interplay of horizontal and vertical motion, with gravity acting downwards. Second, energy conservation explains how the spring's potential energy is converted into the dart's kinetic energy, determining its launch speed. Third, air resistance is a real world force that opposes motion, reducing the dart's range and altering its trajectory. Finally, kinematics provides the equations of motion used to analyze displacement, velocity, and acceleration. Conclusion. By combining experimental data with physics, we determined the dart's initial velocity, estimated air resistance, and linked to the launcher's spring mechanism to the dart's motion. This practical highlights the importance of accounting for real-world factors like air resistance and provides a foundation for more advanced analysis of projectile motion and energy transfer. It also underscores the value of experimentation and validation in understanding physics principles.